In a 1908 electrical engineering textbook published by the International Textbook Company, grounding is introduced as a key safety measure in electrical systems. The textbook illustrates an early understanding of grounding principles. It describes a method where the center tap of an economy coil, also known as an autotransformer, is connected to earth, which is referred to as ground. The purpose of this grounding technique is to reduce the electrical potential, or pressure, of the line conductors to half of their original value in relation to ground. This means that if a fault occurs, the voltage between any conductor and ground will be significantly lower, reducing the risk of electric shock. The concept of a specific resistance value like 25 ohms for grounding is not mentioned in this particular textbook. This indicates that standardized resistance values for grounding were likely developed later as electrical engineering practices evolved. The textbook provides details on lightning protection methods prevalent at the time. Spark gaps are described as a primary means of protecting electrical equipment from lightning strikes. A spark gap consists of two electrodes separated by a small air gap. When a high voltage surge, such as that from a lightning strike, occurs, the voltage exceeds the dielectric strength of the air gap, causing a spark to jump between the electrodes. This spark provides a path for the surge current to flow to ground, diverting it away from sensitive electrical equipment. The textbook serves as a valuable historical document, offering insights into the early stages of electrical engineering. It showcases the gradual development of safety measures and grounding techniques. The introduction of grounding, even in this early form, marks a significant step towards enhancing electrical safety and preventing accidents. The methods and terminologies used in the 1908 textbook reflect the state of electrical engineering knowledge at that time. It is interesting to note the absence of specific resistance values for grounding and the reliance on spark gaps for lightning protection, which were later refined and supplemented with more advanced techniques such as surge arresters. The significance of this textbook lies in its representation of the nascent stages of grounding in electrical systems. It demonstrates how early electrical engineers recognized the importance of grounding as a fundamental safety measure. By connecting the center tap of an autotransformer to ground, they aim to reduce the risk of electrical shock and protect equipment from overvoltage conditions. This early approach to grounding laid the foundation for more sophisticated grounding systems used today. The 1908 textbook also offers valuable insights into the evolution of electrical engineering practices. It reveals how engineers of that era tackled challenges related to overcurrent protection and ground fault detection. The absence of the term 25 ohms suggests that standardized resistance values for grounding were not yet established. Instead, engineers likely relied on empirical methods and practical experience to determine appropriate grounding configurations. Furthermore, the textbook's description of spark gaps as the primary means of lightning protection underscores the limitations of technology at the time. While spark gaps provided a basic level of protection, they were eventually superseded by more advanced surge protection devices that offer better performance and reliability. By studying this historical textbook, modern electrical engineers can gain a deeper appreciation for the progress that has been made in the field. It highlights the importance of continuous innovation and the refinement of existing techniques to improve electrical safety and performance. The textbook also serves as a reminder of the ingenuity and resourcefulness of early electrical engineers who laid the groundwork for the complex electrical systems we rely on today. It is crucial to understand that electrical grounding has evolved significantly since 1908. Modern grounding systems incorporate a variety of components and techniques to ensure safety and prevent electrical hazards. These include ground wires, grounding electrodes, ground fault circuit interrupters or GFCIs, and surge protection devices. Ground wires provide a low impedance path for fault currents to flow back to the source, tripping circuit breakers or fuses too quickly to energize the circuit. Grounding electrodes, such as ground rods or ground plates, establish a connection to the earth, providing a reference point for electrical potential. GFCIs are designed to detect even small imbalances in current between the hot and neutral conductors, indicating a ground fault. When a ground fault is detected, the GFCI quickly interrupts the circuit, preventing electric shock. Surge protection devices, such as surge arresters, protect electrical equipment from voltage surges caused by lightning strikes or other transient events. These devices divert the surge current to ground, preventing damage to sensitive electronic components. The National Electrical Code, or NEC, which is updated every 3 years, provides comprehensive guidelines for electrical installations, including grounding requirements. The NEC specifies the size and type of grounding conductors, the methods for installing grounding electrodes, and the requirements for ground fault protection. Adherence to the NEC is essential for ensuring the safety and reliability of electrical systems. Proper grounding is critical for several reasons. Firstly, it protects people from electric shock by providing a low impedance path for fault currents to flow to ground. Secondly, it helps to prevent damage to electrical equipment by limiting overvoltages and transient surges. Thirdly, it reduces the risk of fire caused by electrical faults. Fourthly, it improves the performance and reliability of electrical systems by minimizing electrical noise and interference. In addition to grounding, overcurrent protection is another essential safety measure in electrical systems. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when it exceeds a predetermined level. This prevents overheating and damage to conductors and equipment, reducing the risk of fire and electrical hazards. Circuit breakers are resettable devices that can be tripped manually or automatically when an overcurrent condition occurs. Fuses are one-time use devices that melt and interrupt the circuit when an overcurrent condition occurs. The selection of appropriate overcurrent protection devices is crucial for ensuring the safety and reliability of electrical systems. The size and type of overcurrent protection device must be carefully matched to the rating of the conductors and equipment being protected. The NEC provides detailed guidelines for selecting overcurrent protection devices based on the application and the specific electrical system. Ground fault detection is another important aspect of electrical safety. Ground faults occur when current flows from a hot conductor to ground through an unintended path. This can happen if insulation is damaged or if a person comes into contact with a live wire. Ground fault circuit interrupters, or GFCIs, are designed to detect even small ground faults and quickly interrupt the circuit, preventing electric shock. GFCIs are commonly used in bathrooms, kitchens, and outdoor locations where there is a higher risk of exposure to water. They are also required for certain types of electrical equipment, such as portable generators and cord and plug-connected appliances. The operation of a GFCI is based on the principle of differential current sensing. The GFCI monitors the current flowing through the hot and neutral conductors. Under normal conditions, the current flowing through the hot conductor is equal to the current flowing through the neutral conductor. However, if a ground fault occurs, some of the current will flow to ground through an unintended path, creating an imbalance between the hot and neutral currents. The GFCI detects this imbalance and quickly interrupts the circuit, typically within a few milliseconds. Lightning protection is another important consideration for electrical systems, particularly in areas that are prone to lightning strikes. Lightning strikes can cause severe damage to electrical equipment and can also pose a significant safety hazard. Lightning protection systems are designed to intercept lightning strikes and safely conduct the current to ground, protecting buildings and equipment from damage. A typical lightning protection system consists of air terminals, conductors, and grounding electrodes. Air terminals, also known as lightning rods, are installed on the roof of a building to intercept lightning strikes. Conductors are used to connect the air terminals to the grounding electrodes, providing a low impedance path for the lightning current to flow to ground. Grounding electrodes, such as ground rods or ground plates, establish a connection to the earth, dissipating the lightning current safely. The design and installation of lightning protection systems must comply with applicable standards and codes, such as the National Fire Protection Association, or NFPA 780. Proper grounding is essential for the effectiveness of a lightning protection system. The grounding electrodes must be properly sized and installed to provide a low impedance path for the lightning current to flow to ground. The grounding system must also be bonded to other metallic structures, such as water pipes and gas pipes, to minimize the risk of side flashes. In summary, grounding is a fundamental safety measure in electrical systems that protects people from electric shock, prevents damage to equipment, reduces the risk of fire, and improves the performance and reliability of electrical systems. Overcurrent protection and ground fault detection are also essential safety measures that work in conjunction with grounding to provide comprehensive protection against electrical hazards. Lightning protection systems are designed to protect buildings and equipment from lightning strikes, which can cause severe damage and pose a significant safety hazard. By understanding the principles of grounding, overcurrent protection, ground fault detection, and lightning protection, electrical engineers and technicians can design, install, and maintain safe and reliable electrical systems.